Hello everyone, in this video I am explaining actinides. So in the previous video of F block elements I have already completed lanthanides. Please watch that video before you watch actinides. Right? Now actinides are part of F block elements. What are F block? We've already covered that, right? So there are 14 actinides. Actinides or actinoids, both are fine. And the atomic number is 90 to 103. So 14 actinides are there. So it lies in which period? It will lie in the 7th period. In 7th period you will find the actinides are present. So when you check, 87 is the first element of the 7th period. 88 is the next element. Then you have 89. So these two are S block. This is D block. And after that you have here 104. So where are those elements of 90 to 103? These elements are present at the bottom of the periodic table, a part of F block elements just below lanthanides. So since F orbital can accommodate 14 electrons, there are 14 actinides present. And in actinides, the 5f orbital is being filled. In lanthanides, as we said, 4f orbital is being filled. In actinides, 5f orbital is being filled. So 90 to 103, these are actinides present at the bottom of the periodic table. Now if we write the general configuration, it will be radon, that is 86 atomic number. 86, the last element of 6th period. Then you have 7th period first element. Then these two are filled, means 7s2 is filled. So we write the configuration 7s2. Radon is already there, that is completed. Then you have 7s2. Then you have 6d1. 6d, 0, at times it's there because there are a lot of abnormal configurations in actinides too. So 6d, 0 to 1, and then comes 5f, 1 to 14. Right, so the configuration becomes radon, then 7s2, 6d, 0 to 1, and 5f, 1 to 14. So since when we are writing the configuration, we are writing the inner shells first and then the outer shells. So we have written in this manner. 5f, 1 to 14, after radon, then 6d, 0 to 1, 7s2. Fine with the configuration? Now just have a look at the configurations of actinides. Right? So in the complete screen you have the configurations. Actinium. Actinium is a member of D block. Thorium is the first member of actinoids. So 90 to 103. Lawrencium is the last one. Right? So check the configurations. Radon. This is 5f0. D2 it becomes. Just check, in the whole series only the first element is having D2. It is not having any electron in 5f. This is again abnormality. Then you will find F2, D1 again comes back. Then 3, 4, 5. 5 is missing in between. At times it is missing. Then you have 7. Again 7. D1 again comes back. And so on. You will find that there are a lot of abnormal configurations in actinides, just like lanthanides. The reason for why they are having so many abnormal configurations, the valence orbitals 7s, 6d and 5f, they have comparable energies. So when they have comparable energies, all can take part in the bond formation. At times one of the orbital particularly acquires less energy. So mainly this is not participating here. The last ones, these get mainly affected. So you will have these two energies are almost comparable, and at times 5f becomes less and at times 6d becomes lesser than 5f. So just check the configuration. Here again in the last one you have, this is 6d1. 6d1, 7s2, 4f14, the last element. Fine. Now we move on to the properties. Ionization enthalpy, the first property. Now ionization enthalpy, when you check for the actinides, is not known accurately. The values are not really known, but they are lesser than lanthanides. This is to be underlined. Ionization enthalpy of actinides are much lower They are lower than the early lanthanides. Why? Because in actinides, the 5f orbital is being filled, and we know the 5f orbitals penetrate less towards the nucleus. Yes, it is penetrating less into the inner core of the electrons. Therefore, we can say that the 4f electrons are closer to the nucleus. 4f electrons are closer. Therefore, it is very difficult to remove electrons from the lanthanides than from actinides. So, what you write is that for 5f orbitals, they penetrate less into the inner core of the electrons, and therefore they are most strongly shielded from the nuclear charge, okay, than 4f of the corresponding lanthanides, right? Next property, physical property. Melting and boiling point of actinides are moderately high. They are lower than the transition elements. Okay, they are comparatively high because the size is small, but lower than the transition elements, and there is no regular trend found. So no trend means we don't have to bother about increasing or decreasing part. Right? Density. Density of the actinide is first increasing and then it decreases. First increases and then decreases. It all depends upon the size variation. Now, moving on to the oxidation state. Oxidation state, most common one is 3, just like lanthanides. But in lanthanides, we said apart from 3, 2 and 4 are the oxidation states. But in actinides, you say there are all type of the oxidation states shown by actinides. 2, 3, 4, 5, 6, 7. They show all. Why? Why actinides show so many oxidation states? Because this is the answer for it. 5f, 6d and 7s. They have comparable energies. So when they have comparable energies, all these 3 shells electrons can participate in the bond formation. That is why they show large number of the oxidation states. However, the most stable one is plus 3 oxidation state. Got it? Yeah, further about the oxidation states. In the first half of the actinide series, what we find is they are exhibiting higher oxidation states. That means till neptunium. Neptunium is having the maximum, right? And after neptunium, you will find that the number of the oxidation states are decreasing. Like for example, thorium. Thorium can show 4. Then next one is 5, 6, 7 in Pa, U and Np. Is this part clear? Okay. Then further you find that after Np, the number of the maximum oxidation state will decrease. Then moving on to the next important property, that is actinide contraction. Like we have lanthanide contraction, you have this thing actinide also. The steady decrease in the ionic radii with increase in the atomic number is called as actinide contraction. Okay, it is steadily decreasing. Why it decreases? The same answer as we did in lanthanides. In these, 5f orbital is in the process of being filled. Because of the peculiar shape of the f orbital, it is not able to provide effective shielding. Okay, so because of the imperfect shielding of the f orbital, the effective nuclear charge will increase. Shielding is not there, effective nuclear charge will increase. As a result, the size will decrease. So this is the cause. It's a very, very important part. You know, what is actinide contraction? What is actinide contraction? What are the causes? And this part. Actinide contraction is greater than lanthanide contraction. Though in both f orbital is being filled. So here we will have to check. In lanthanides, 4f orbital is in the process of being filled. In actinides, the 5f orbital is in the process of being filled. Okay, so which is in comparison, if you say, which is more poorly shielded? 5f. It is due to the poor shielding of the 5f electrons, because the 5f electrons are present away from the nucleus. 4f electrons are deep buried inside the nucleus. So there is poor shielding of the 5f orbital electrons, which results in more nuclear charge present in case of the actinides. That is why the actinide contraction is greater than the lanthanide contraction. Very, very, very important part. What is actinide contraction? What are the causes? And actinide contraction is greater than the lanthanide contraction. Okay, please, I am telling you, make notes side by side. You can pause it in between and make notes. Clear? Yeah. Moving on to the next property, magnetic property. Most of the actinide ions are paramagnetic because they have unpaired electrons. But if they have F0 or F14 configuration wherein F is paired, it will be diamagnetic. In rest all the cases, it will be paramagnetic. Color, same like the previous study. It says if there are unpaired electrons, they will be colored. So actinide ions are generally colored, and the color depends upon the number of the F electrons, 5F electrons. If they are containing F0 and F7, we will check in the tabular column, then it will be colorless. And why there is a color? Because of FF transition. It arises due to the electronic transition between various energy states within 5F subshell. That is termed as FF transition. So due to which actinides exhibit color. Right? Now just have a look at this tabular column. Though you're not expected to learn the color, that is just for reference. You can check in these are the ions given. This is the configuration. How many electrons are there in the F orbital? On that basis, what you can see? If it is 0 or 7, it is colorless. Rest all cases, it is colored. You can just go through the color part. Right? Yeah, the next property is formation of complexes. Like lanthanides, even actinides have the tendency to form complexes. Though actinides have a greater tendency to form complexes. All these can be, simple 1-1 mark questions asked. Give reason why actinides have more tendency to form the complexes. Recently we have studied actinide contraction is greater than lanthanide contraction. Why? Because the size was small. F5F orbitals are more poorly shielded. So same is the answer for them. They have smaller size and higher charge. That is why actinides have more tendency to form the complexes. Fine. Chemical properties. Now check for the chemical properties. If you talk about their metals, they are all silvery white metals. Highly reactive, especially of course when they are in the finely divided form. When they are in the divided form, then surface area will be more, obviously the reactivity has to increase. They react with boiling water and form oxides and hydrides. They react with non-metals at a moderate temperature. All metals are attacked by HCl, and most of these are slightly affected by nitric acid due to the formation of the protective oxide layer. This is a similarity with aluminium, similarity with the beryllium, which form a protective coating. Got it? Now, we are coming on to the most important part of this similarities between lanthanides and actinides, and at the same time we will also study their differences. These are the similarities. Both exhibit +3 oxidation state predominantly. Though they also exhibit some other oxidation states, but predominantly the most common oxidation state exhibited in both is 3. In both, the F orbital is being filled. Not 5, that 4F is for this and 5F is for this. But though we can say, the F orbital is being filled in both. Yes, both lanthanides and actinides having the same number of the unpaired electron, they have a similar spectra. Similar spectra, absorption and the emission spectra we are talking about. They'll have a similar type of the spectra if they contain the same number of unpaired electrons. Right? Both are electropositive, highly reactive. Like lanthanide contraction, there is actinide contraction also. Because of the poor shielding of 4F and 5F. Though we have studied that 5F is more poorly shielded because it is away from the nucleus. This is closer to the nucleus. So here the shielding will be slightly more. But though they are exhibiting that contraction concept. Next, this is general property part. If you don't remember this, it is fine. The first few ones are okay. Okay, the nitrates, it's comma here, perchlorates and sulfates of trivalent actinides and lanthanides, they are soluble, whereas hydroxide, chloride and carbonate are insoluble. So similarity between the two. Actinides like lanthanide, they show ion exchange behavior. Got it? Now we move on to the last topic, that is differences between lanthanides and actinides. Yeah, here are the differences. Lanthanides, actinides. Oxidation state terms, both show 3, but in this 2 and 4 are also shown. Here all 4, 5, 6, 7, all. Even 2 is shown in this. All are shown. Binding energies of 4F is higher and 5F is lower. So it's a difference between the two. Shielding effect, 4F has greater shielding in comparison to 5F. Okay, that reason part we have already done, but it's a difference between the two. Both have tendency to form complexes, but this is lesser tendency and this one has more tendency to form complexes. So you can make a tabular column in your notebook. Okay, so when you're noting down, you're making notes, obviously you will be able to remember them in a better manner. Basic character. Lanthanide compounds are less basic and actinides are more basic. So far we have done 5. So some more differences are there. Yeah, further the differences are the tendency to form oxoions. Lanthanides do not have the tendency to form oxoions. Actinides have the tendency to form. So some of the examples are these. It is UO2. It is like this. UO2 and plus. This is PuO2 and plus. Okay, they have the tendency to form oxoions. These do not. And in lanthanides, except promethium, rest all lanthanides are non-radioactive. Whereas all actinides are radioactive. Color, most of the ions are colored, colorless. Actually here we can say if they are containing unpaired electrons, even in lanthanides, if they contain unpaired electrons, they will be colored. But if you compare just the number wise, here more number are colored. Even lanthanides are colored if they have unpaired electrons in f orbital. But if you compare the number, most of them are colored. In actinides, here little lesser number, not colorless. Completely colorless they will not be having. Okay, if it is having unpaired, then it will be colored. Then otherwise it will be colorless. But if you compare the number, more number is colored in actinides. Magnetic properties, both are paramagnetic, that is fine. But magnetic properties can be easily explained here, and in actinides it cannot be explained easily. Okay, now with this we have completed the F block elements. Please make notes and learn it. Thank you.